Okay, today let's talk about section 7, counting zeros, the open mapping theorem. Okay, so we already have the Cauchy integral theorem, and we want to see some application of this very important theorem. In the past section, we know that if f is analytic, it has a 0. Then f of z can be written as a z minus a to mth power times g of z, with g of z analytic and g of a is not equal to 0. Here the m is called the multiplicity of this 0 a. Okay, and if G is a region open connected and F is analytic with zeros A1, AM, possibly with a multiplicity. We repeat it. If it is repeated according to the multiplicity of the 0. Of the zeros. Okay, so possibly it's like A1, 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 and then A2, 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 A2. Okay, and if this happens, we can write f of z as a z minus a1, z minus a2, z minus am times g of z. Okay, so it's a product, and the first few terms are just linear factors, and the last one is g, and g of z is analytic. Remember, g of z is analytic, and so g of z is analytic, and the g of z is never equal to 0 for every point inside G. If g of z is 0 for some other point, then f will have another 0. So here, let's just assume there's a finitely many zeros. Okay, if this happens, then we can differentiate f. Then you will have a product rule, and we form the ratio between f prime and f. With a simple computation, you will see that this ratio becomes 1 over z minus a1 plus 1 over z minus a2 plus 1 over z minus am and plus g prime of z over g of z. Okay, and you can just try the product rule and divide by the product. You will see this pattern. And clearly here, z is not equal to a1, a2, am, and z has no restriction about the from g of z. Okay. Okay, so we have such decomposition of f prime and f. With this decomposition, we do the integral along certain closed rectifiable curve, and we will get the following theorem. Okay, so let G be a region. And let f be an analytic function. On G with zeros A1 up to AM repeated according to multiplicity. If gamma is a closed rectifiable curve in G, which does not pass through any point AK, and if gamma is homologous to 0. Homologous to 0, remember what is homologous to 0? It means the winding number of gamma with respect to W is always 0 for all W inside G, C minus G. So this is homologous. We introduced this definition, this concept in last lecture. Okay, so we can ignore this long expression, but just say homologous. Then the integral of f prime of z over f of z along gamma divided by 1 over 2 pi I is equal to the sigma, the winding number with respect to AK, k from 1 to n. Okay, so that's the statement. Well, this statement is just a trivial application of the Cauchy integral formula. Okay, so here G is analytic. G is not equal to 0. G prime is analytic, and so this last ratio is analytic function. And the Cauchy integral theorem says if you have a homologous to 0 curve, then this integral is 0. This integral vanishes. Cauchy theorem. And the first few terms just provide the winding number by the definition. Right? So that's exactly the application of integral and the Cauchy theorem. Winding number is a special case of Cauchy integral formula. Okay. Okay, so we have this computation. The integral of f prime over f is divided by 2 pi I is always a sum of the winding number. And here, because we are talking about a closed rectifiable curve, then inside the closed rectifiable curve, there are at most finitely many zeros. So possibly this f has infinitely many zeros, but the zero will converge to the boundary. So inside the closed rectifiable curve, there are only finitely many zeros. So here, this f may not just contain those zeros, but for most of the zeros, the winding number will vanish, so it doesn't matter how many zeros you mention. It has finitely many or infinitely many. Okay. Theorem or corollary. Let's say corollary. We adapt these conditions, and we modify this 0 a little bit. Okay, so let f, g, and gamma be as in the preceding theorem, except that A1, AM are the points in G that satisfy the equation Fz is equal to alpha, not A. Fz is equal to alpha. Here, 0 means Fz is equal to 0. Okay, so this place you get the zeros, then Fz is equal to 0. And this place we replace 0 by alpha, whatever complex number alpha. Then we have 1 over 2 pi I, the integral along gamma f prime of z over. Then this denominator is f of z. It is actually f of z minus 0. Here it is f of z minus alpha. Okay, so this is also equal to the sum of the winding number with respect to AK. With respect to AK. So you just consider this one as your new analytic function. You call it g of z. Then f prime is equal to g prime. You apply the preceding theorem. You will get the answer. Okay? So that's not the a big step. It's just a small modification. Okay? So we don't just study the 0. We study the solution of Fz is equal to alpha. Okay, so now let's use this corollary to another corollary. Let's use the theorem to compute some integral. Okay, assume we have the integral 2z plus 1 over z squared plus z plus 1, where gamma is a circle centered at the origin with radius 2. Okay, and let's check. First, the numerator is the derivative of the denominator, so f prime over f. And second, this is if you factor it, you can see it. How do we know this is like this way? Z squared plus z plus 1 is, you use z minus 1. So the z cubed minus 1 and over z minus 1. And z cubed minus 1 has 3 zeros. What are 3 zeros? So e to 3, 2k pi I. K is 0, 1, and 2. Right? So when k is 0, it's 1. It corresponds to this one. This is the unique, the real zeros. When k is 1, you get this one. 1k is 2, you get this one. So if you factor this, you will get these two terms. Okay, so they are the two non-real cubic roots of 1. Non-real cubic roots of 1. Okay, whatever, it's just two numbers, and those two numbers have Ab's value 1, so they're inside the circle. They are inside the closed rectifiable curve gamma. And because this is a simple curve, one in number, let's assume it is a counterclockwise. Okay, then the integral is going to be here. There's no over 2 pi I, so it's a 2 pi I times a one in number of gamma with respect to let's call it W1 and W2. W1 plus a one in number W2. Counterclockwise, then you have 1 and 1, so it's a 4 pi. Right? So it's a well, and this is very artificial. It's artificial example, so we just quickly find the answer. Okay. And remember, this sum is always a finite sum. It's not a series. It's not a series. Most of the terms will be 0. Okay, now let's see a little bit discussion before we present the next theorem. We have two regions, so we have region G, and we have a 0, 1 gamma closed rectifiable. And from region G, we have an analytic function f. F maps this closed rectifiable curve to another closed rectifiable curve. And this, the composite function, is called sigma. Closed is not a problem. So basically, you need to prove that this is rectifiable. Rectifiable. Of course, here we assume this is analytic. If you have an analytic map, it will map a rectifiable curve to a rectifiable curve. So this is one of the exercises. You should try it. Okay, so this is a rectifiable curve. And then let's say we have a point here. A point alpha is here. The point alpha has several preimages. So you have a preimage here, a preimage here, preimage here, here, here. There's several preimages. A1, A2, A3, A4, A5. Okay, the preimage. Now let's try to compute some Wanting number. So you have this curve, you talk about the Wanting number. Whenever you talk about Wanding number, we assume this is homologous to 0 in order to apply the whatever theorem we already have. So we assume this gamma is homologous to 0. The Wanding number of sigma with respect to alpha, by definition, 1 over 2 pi I. Here, let's use W. This place, let's use Z, variable Z. And W minus alpha along sigma. With a little bit computation, like the differential and stuff, with a little bit computation, W is f of Z. So it's f prime of Z dz. F of Z minus alpha. When we talk about alpha, Z, it is over the domain, so it's along gamma. And here, there's a small computation. You need to verify these two things are the same. Okay, so we have this. And this one is the formula in the corollary. So it is equal to sigma k from 1 to m, the Wanding number of gamma with respect to ak. With respect to ak. Okay, so again, maybe there are infinitely many points here, but still non-zero term are finitely many, because if a function has infinitely many solutions, that sequence will converge to the boundary. So when we get a closed rectifiable curve, it will surround only finitely many points. Okay, so okay, so that's not here. It's not a problem for us to just label finitely many, not infinitely many. Okay, so the Wanding number for the image point is the sum of the Wanding number for the pre-image. Okay, so that's one observation. The Wanding number for the image is the sum of the Wanding number for the pre-image. Then let's check. When you have this alpha, and this curve divides the complex plane into several connected components, assume that beta and alpha belong to the same component of complex plane, but without this sigma. This should be the sigma. Yeah, it's here. It's here. This is sigma. From here to here is sigma. Here is alpha. Okay, this is sigma part. If they belong to the same connected component of C without the trace of sigma, then the Wanding number of sigma with respect to alpha is equal to the winding number of sigma with respect to beta. So it's a winding number is a constant for over each connected component. Winding number is 0 over that unbounded component. Okay. Okay, then you see this one is equal to sigma n gamma, the zeros, let's say the zeros of alpha, k from 1 to m. And here this one is equal to sigma winding number gamma z j beta, the zeros of a beta, j from 1 to m. Let's just pick up the largest index, where zk alpha, zj beta are the points in G, in the domain of G, that satisfy fz is equal to alpha and fz is equal to beta respectively. Okay. Okay. So that's so we have this. This one is equal to this. If we choose gamma, the original gamma, so that the winding number of gamma with respect to zk alpha is equal to 1 for each k. For each solution, you just get a 1. Then what do we say? We can see the information about the number of solution fz equal to beta. So you know something about here. You go through this line, you can get the solution, the information of a solution about this part. So that's basically what the process talks about. Because you first only know the information about one point. We want to know the information about the point from the neighborhood when beta is close to alpha, at least in the same connected component. Okay, so that's what we just discussed. Okay, so to summarize this, we see the theorem. The theorem is the following. Suppose F is analytic in BAR. So it's analytic in the open disk centered at A with radius R, and let alpha be f of A. So alpha is f of A. So you map the center to certain alpha. If fz minus alpha has a 0 of order m at z equal to A, then there is an epsilon greater than 0 and delta greater than 0, epsilon delta both greater than 0, such that for eta minus alpha less than delta. When eta is close to the image, alpha is the image. When eta is close to the image, the equation fz equal to eta has exactly m is this m, order m, has exactly m simple roots inside the b, a, and epsilon. Okay, so we know there is an order m0, then in the neighborhood of the image, not a zero, solution, order m solution, then in the neighborhood of the image, all the solutions are simple solution, and there are m simple solution. It's kind of you untie the multiple solution to the simple solution. Okay, so how do we show it? Okay, so here a simple root of fz equal to eta is a zero of fz minus eta of multiplicity 1. In other words, fz is eta plus z minus a times g of z, where g of a is not equal to 0. Okay, so that's a simple root. And the fz minus alpha has a 0 of finite multiplicity. Finite multiplicity, so fz is equal to alpha plus z minus a to m times g of z. It has such an expression. This implies f is not constant, not a constant function. F is not a constant, it has to be like this. Okay, so that's a remark before we prove it. Let's try the proof. Okay. So basically, you see, this is the original domain centered at A with radius capital R. We're going to shrink it, so we will have a smaller region with a certain required condition. And inside the smaller region, we're going to draw a closed rectifiable curve. We're going to draw the closed rectifiable curve. The safe way to draw the closed rectifiable curve inside this circle is that we just choose half of the radius. Okay, so you see, this is going to be half of the radius of the smaller disk. This is original large disk. So this one we are going to eventually call it epsilon. Then we require the twice of epsilon is smaller than r. Okay, so that's the reason behind the following definition. Okay, and so since the zeros of an analytic function are isolated, we can choose alpha positive such that epsilon positive, epsilon positive such that epsilon is less than 1/2 of r. We require twice of epsilon is less than r. Okay, so this is an epsilon condition. Epsilon. The condition is that f of z equal to alpha has no solutions with z minus a less than twice of epsilon and greater than 0. So inside this smaller disk, smaller open disk, a is a unique 0, unique solution. This is an isolation. Okay, so that's a one condition. Second, before we state the second condition, let's discuss the situation. So in the theorem, we say this A has an order m. M can be 1, m can be greater than or equal to 2. 1 or bigger than 1. If m is 1, here, let's check the case. If m is 1, so what is f prime of z? M is 1 here. M is equal to 1. M is equal to 1. Let's check f prime. Eta, the derivative is 0. So we apply the product. We will get a g of z plus z minus a times a g prime of z. Okay, so this is the derivative. If it's derivative, then we evaluate f prime of a. We evaluate at a, we will get g of a. This is 0. It's not equal to 0. Okay, so at g of a is not equal to 0. If m is greater than or equal to 2, then what is f prime? Greater than or equal to 2, the formula is like this. So we differentiate the term. This is still 0. The constant term always disappear. You differentiate the second part. The second part will have m z minus a, m minus 1, and g of z, and plus z minus a, m, g prime of z. Okay, so f prime of a. F prime of a, let's check here. You have z minus a here, z minus a here. F prime of a is equal to 0. So the multiplicity 1, the f prime of a is not 0. Multiplicity greater than or equal to 2, the f prime of a is equal to 0. If it is not 0, by the continuity, there is a neighborhood, so that inside the neighborhood, f prime of z is not equal to 0, including a. If f prime of a is 0, by the isolation of the zeros, then f prime of z is not equal to 0 in this disk, but without a. Without a. A is a unique 0. Okay? Either way, we can choose a small enough epsilon so that in this disk, we exclude the center. In this disk, f prime of z is not equal to 0. Okay, so in both cases, f prime of z is not equal to 0. So the m equal to 1, you can include the 0. M is greater than 1, you have to remove the 0. So anyway, we don't care about the point A. So we always assume it is greater than 0. Okay, so that's a condition for the epsilon. First, inside the disk, there's only 1 0. Second, inside disk, f prime of a, punctured disk, f prime of z is not equal to 0. Okay, now let's pick up the gamma. So let gamma be a plus epsilon e 2 pi I t. T is between 0 and 1. okay, counterclockwise oriented, and it's a simple curve. The winding number is either 1 or 0. And let sigma be f circle gamma. Okay, and alpha does not belong to the trace of sigma. Alpha is in the center. Okay. Then there is a delta greater than 0 such that the ball centered at alpha with radius delta intersect the trace sigma is empty. So here, why this alpha is not in the trace of sigma? You see here, sigma, this is if it is inside the trace of sigma, it means it will have a solution over this closed disk. But we just assume fz equal to alpha has only solution at A, so there's no solution around the circle. So that's why alpha is not inside the trace of sigma. Sigma is a compact set. Whenever you have a point off the compact set, the distance is strictly positive. So you find a delta so that sigma is like this and alpha is here. This is delta. The distance is delta. Okay. Then this is a connected set. The connected set, it is totally contained in the same component of C without the trace of sigma, because it does not intersect the boundary. So the sigma is a boundary. Okay, and if you have cosine minus alpha less than delta, if you have a eta, sorry, this is eta. If you have an eta inside this open disk, then the winding number of sigma with respect to alpha is equal to the winding number of sigma with respect to eta. They have the same winding number. And then it is equal to the sigma, the winding number with respect to the solutions of eta. Solutions of eta. P. Let's not use M. M is already used. Let's use a letter P. Okay. The winding number of gamma with respect to Z is 0 or 1. Z is inside gamma. Z is outside gamma. So we have this the winding number alpha, this is equal to M. This is equal to M. Because you have M solutions and you have each one is 1, so you add all them together, it is equal to 1. And this part, this is also 1. So this P is equal to 1. This implies, P is equal to M. There are M solutions of Fz equal to eta. Okay, so here this one is equal to M. So this part is M. And this part is M. You go to this place. This is either 1 or 0. So you must have P equal to M. And we only know, so far we only know there are M solutions. But since F prime of Z is not equal to 0, F prime of Z not equal to 0 for Z minus A between 0 and epsilon. If it's not equal to 0, there's no repeated solutions. So M solutions, no repeated. All solutions are simple. All solutions are simple. So that's the end of the proof. Okay, so all solutions are simple solutions, and there are exactly M simple solutions. Right? Okay, so from this part, let's see one more stuff from this part. What we just proved, we prove if eta belongs to the ball centered at alpha with a radius delta, then Fz equal to eta. We don't emphasize the numbers. We just say Fz equal to eta has solutions. So it means the ball centered at alpha with radius delta is inside the image of the ball centered at A with radius epsilon. Right? It is like this. So this is the original domain. So the alpha is f of A. So the image point has a neighborhood, open neighborhood inside the image. It means this is open. Not this one. This must be open. Okay, so that's the open mapping theorem. The open mapping theorem says let G be a region and suppose that f is a non-constant analytic function on G, then for any open set U in G, Fu is open. So the image of open set is open. This is not a trivial fact, because we know that the pre-image of open set is always open. That's for the continuity. Here, the analytic non-constant function says it maps open set to open set. it's called an open map. Okay, maps open to open is called an open map. Okay, so the proof is actually this part. The proof is actually this part. So U is open for any point A in U. There exists R such that the ball BAR is inside the U. Okay, then by the previous computation, there is a delta such that the BFA delta is inside the is inside the FBAR is inside F of U. So every point there is a neighborhood open disk, so that is contained in the image FU. Then FU is open. All the points are the interior point. Okay. So that's the end of the proof. That's the end of the proof. And here let's get some topology here. F maps open set to open sets. F is called an open map. If in addition F is 1-to-1, in addition means it's open 1-to-1, then F inverse is continuous. F inverse is continuous. So that's the relation between the open map and the inverse map, the continuity of the inverse map. And because of this, we can have the following simple corollary at the end of this section. Suppose F from G to C is 1-to-1 analytic, and Fg is omega. Then F inverse from omega to C is analytic, and F inverse prime of W is 1 over F prime of Z, where W is F of Z. Where W is F of Z. Okay. Well, this proof is just a chain rule, and we actually did the proof, and you just go through this, and you will get it. In fact, you just go through this, you will get the result. Okay, and the proposition, we don't go through the proposition, is a proposition chapter 3 2.20. Chapter 3 2.20. Okay, so we stop here today.